Morning. Always. Yes.
This is Sarah. Quick question before we begin.
Hi, Sarah.
I've got a 10 o'clock medical appointment, so I'm probably got to drop off. How do we access the the recorded copies of past exercises to catch up on the second half today? Where do we access that?
You're asking about the record. The recording should be available like
recording.
later this afternoon. Yeah.
Yeah, just on Canvas or where exactly?
Yeah. So all the Zoom recordings from all of the lectures, if you go into Canvas and you go to Zoom, you'll see a link, a tab for cloud recordings. They're all going to be there. Yeah.
Oh, perfect. I see it now. I just didn't click on the correct tab. Thanks.
Yep. All right, we'll get started in about a minute or so here. Okay, well, good morning, everyone. I want to wish everybody a happy Juneteenth. So those of you unfamiliar with the idea of Juneteenth, this is a federal holiday in the United States. So question is, should we really be here right now? But no, it's a federal holiday that celebrates the ending of slavery in the United States. So it's a very important holiday in the broader context of the history in this country. So actually all federal employees in the United States have the day off today for this holiday. So it's important to observe this, no matter what state you're coming from. So big holiday in this country. I want to start today with going over homework number 2. Everybody, you've received your scores on homework number 2 at this point, including comments and feedback from Young Chow. So I want to talk about a couple of issues that came up repeatedly as we were reviewing the different homework submissions. I also want to thank everybody for submitting your prospectus paragraphs. At this point, everybody should have received feedback on those prospectus paragraphs. So definitely follow up if my comments and questions were unclear or it's not certain where you're going with the work at this point. Definitely follow up and feel free to set up a meeting with me if you'd like to go over the work that your team or that you are doing on the final project. Be more than happy to continue corresponding with you about the work that you're doing. But let me know if any of my comments and feedback were unclear in response to the submission. So, but people are working on a very diverse set of projects, different data sets, different analysis objectives. I think this is going to make for a very nice collection of final projects. I'm really looking forward to seeing where the work leads on each of your projects. So thank you again for submitting those. Okay, so homework number 2, for the most part, people again did pretty well. There were just a couple repeated issues, like I said, that came up that I want to touch on with respect to what this homework was really allowing you to do. So first one that seemed to come up a handful of times is the idea that when you're computing a weighted estimate, some of you were actually computing a variable that was the weight multiplied by the actual values on the survey variable, and then submitting that variable, that new variable, to a weighted analysis. That's overkill, right? When you do that, you're effectively double weighting. So I wanted to bring back this slide from module number 2 that talks about how survey weighted estimates are constructed, right? Remember, we're just multiplying each individual's contribution to the estimate by that final survey weight in the data set to form a population estimate of whatever that parameter is, right? That's the theory, that's the concept. When you are using Stata or R or whatever the case may be, and you use or you specify a weight variable in survey set, or when you create your survey design object or whatever the case may be, the software will do that for you. And I'm sorry if people missed this point, but when you turn on, quote unquote, a weight variable in one of these analyses, all of your estimates will be computed exactly like you see here, with each individual's contribution being multiplied by their weight. You don't actually have to do that physically when you're analyzing the data. That's the whole point of specifying a weight variable in the first place. So if you computed, for example, in the case of a weighted mean, if you computed a new variable that was equal to the variable times the weight, you save that in the data set, and then you input that to a weighted procedure, effectively what you were doing was weight squared times y divided by the sum of the weight squared. So that came up a couple times, and again, that's completely unnecessary, right? Because that's the whole reason we have these specialized survey procedures in the first place. They allow you to specify a weight variable. You actually don't have to do that calculation on your own. Okay, so when you specify a weight variable, weighted estimates of the parameters will be computed. Okay, so that came up a couple times, and Young Chow and I were a little bit surprised by that. But when you turn on a weight variable in survey set or survey design or whatever procedure you're using, the software will take care of the calculation of these weighted estimates for you. You don't have to create weighted versions of each variable on your own. Okay, is everybody clear on that point? Sorry if we missed communicating that, but I want to make sure everybody understands that particular point, because this came up on a handful of the assignments. Okay, so everybody's good? Okay, so no need to double weight like I was saying. Second issue that came up, which I think was the other biggest point, was this problem, or basically the pair of problems here. One problem was asking you to compute weighted estimates of the mean without any kind of design adjustments to the standard error. And a couple of you emailed me about that regarding clarification about what we meant. But basically what this problem was saying was do what the vast majority of analysts do when conducting analyses of these data sets. That is, turn on the weight, make sure you specify the weight to the procedure, but naively ignore the stratification and cluster sampling or the replicate weights. Okay, the additional codes that we've talked about that are important for variance estimation. So the problem was forcing you to make that mistake. Okay, not adjust for the design when computing the standard errors, so that you could compare the standard errors across these different approaches. Okay, so part D was basically saying, look at that weighted mean. Here's one way you could do it, right? Simply use the mean command within Stata and just specify the p weight, and that's it. Or just use survey set, turn on the p weight, and ignore the cluster and stratum codes. That's another way you can do it. Okay? That's going to give you the weighted point estimate, but incorrect standard errors. So the design corrected standard errors are those that fully adjust for not only the weighting, but the stratification and the cluster sampling. That's what we mean by those design corrections or design adjustments. Okay, so that is what you were doing down here with part E. You were calculating the same point estimates. Those didn't change when using the weights and estimation, assuming you didn't double weight. So those don't change. You were calculating linearized and jackknife standard errors to compare with what you would see ignoring the stratification, the cluster sampling. And you can see in the case of comparing the results for part D and part E, there's a very notable difference in the standard errors. Okay, they definitely increase when you're fully adjusting for the cluster sampling and the stratification, okay, as we would expect. Okay, any questions about that point? Okay. Whenever we're referring to design adjusted standard errors, they're fully adjusting for not just the weights, but also the stratification and the cluster sampling. Okay. So I think those were the two primary issues that emerged. For the most part, people got all the other problems that we were looking at here correct, including the design effect issues. But if you have questions about anything else or any comments or marks that you receive on your homework, definitely send us a follow-up and we can correspond further about that. But I think those are the two main issues. Okay. Questions, comments? Okay, we just released the scores, so you may not have had a chance to review yet, but take a look today, later on this week, and let me know if you have any questions. You have Jupiter?
I think maybe you can just comment on the impact, the weighted okay, the weights can have on the graphs, because we're using these normalized weights.
Right.
So if you trim the decimal places, then you are basically having, because you have to use, I don't know what to use, maybe.
Yeah, so in Stata, if you're making a histogram, you would have to use an F weight, correct? So trimming off the decimals of these weights is not going to make a major difference in the appearance of a weighted histogram, right? Same thing with normalized weights, okay? That's not going to make a difference. Remember, with normalized weights, the only statistic that gets affected is a total. Okay? So here, what we're basically doing is we're calculating the proportions of the population that fall into each of these windows on that particular variable. Okay? Proportions, weighted proportions, it doesn't matter if the weights are normalized. Okay? The only statistic that's going to be affected by a normalized weight is a total.
I wasn't very sure because we gained quite a number of zero weights. Mm-hmm. And so I did not think of the computations that how it can affect the bars looked similar. I wasn't really sure in the background.
Right. So that's the case if you do have a normalized weight and you round like this, that's the case where you could have an issue with having too many zeros. Okay. So that's where we do have to be careful. But in general, when you're using a normalized weight, proportions, means, they're not going to be affected. Okay, that's the important distinction here. Okay. Good question. Okay, other questions on the homework? Any other questions on the homework? Yep.
Will you share the solutions with us?
Say again?
Will you share these?
Guys, I can't hear them, so.
Will you share these solutions with us?
Yeah, they're gonna be posted. We just released the homework about a half an hour ago, so I'll post the solutions after the lecture this morning.
All right.
Yep. Okay, other questions about the homework? Yep. What's that?
Even the ones.
They've been up there for about a week and a half now. Yeah. Yeah, so just as a reminder, if you go into Canvas, you're gonna see all the files for the course in these different folders. So if you go into homework exercises, you'll see the homework 1 solutions as part of that folder. We just were going over the solutions earlier this morning, so we haven't yet posted those to the folder, but this is where you'll see them. Okay. Other questions? Okay. Okay, but again, everybody's doing very well in the homework. Just the one point I would make is if some of you were confused by that language, like design corrected, or what exactly the parts of the homework are asking about, don't hesitate to email. Okay, again, I think some of you got tripped up by that language, but if there's any uncertainty about what these exercises are asking for, just send a quick note. Okay, that's what we're here for. So. Okay, so let's turn to today's lecture module. So this is lecture module 7. Today, our primary focus is going to be on percentiles, subpopulation analysis, and functions of estimates. So this is really the last lecture that's going to be involving descriptive estimation. Starting next week, we're going to turn to multivariable modeling. Okay, thinking about different types of regression models, linear regression, logistic regression, generalized linear models. So we're going to turn to a multivariable approaches starting next week. This is the last lecture on descriptive approaches. So we're going to be talking about some specialized types of descriptive analyses that come up quite often when you're analyzing survey data today. Okay, so first, percentiles. So thus far in the course, we've been talking about estimation of means, proportions, estimation of standard deviations, if that's something you wish to estimate describing a population. But these aren't the only ways to describe the distribution of some variable in a population. Another very important quantity for describing the distribution of a variable is the percentile. So analysts are often interested in more than just the mean or other measures of central tendency to describe an overall distribution. These percentiles are often very valuable for understanding some larger population distribution. So for example, you might be interested in the 95th percentile of prostate-specific antigen levels in a national sample of men over age 40. This is a very good indicator of whether or not you might have prostate cancer. Okay, so that's an important test that gets performed in men over the age of 40. And practicing doctors, physicians might want to know what's that extremely high level of PSA score that would say somebody is definitely at risk of prostate cancer. And so all of those kinds of estimates are like growth charts. If you take your child to the doctor's office, the pediatrician, and you see different levels of growth at different ages, those are all based on weighted estimates from health surveys. Okay. All of those growth charts come from national surveys that collect information on kids, how much they weigh. In this case, collecting information on men over the age of 40. What are their PSA scores? See what that distribution looks like. See what the unusual values are at the extreme of that distribution. Okay. So you might also be interested in median values on continuous variables. We've been focusing on the mean, but the mean can be easily affected by extreme values on the distributions of these variables. You may also wish to summarize the central tendency of a continuous variable using the median. And this is often the case with financial variables like total household assets, household income, things like that. So for skewed variables, to describe the central tendency of the population, you may want to compute a median. You may want to compute quartiles, right? What's the first quartile? The 25th percentile, the median, the 75th percentile on test scores or systolic blood pressure for a very specific subgroup of the population. And these are all very common descriptive analysis tasks, but there are important considerations when we're analyzing complex sample survey data that we need to think about when calculating these types of percentiles. And that's why we haven't started talking about them until now. Okay, so that's going to be our initial focus here. Okay, so we need a specialized estimation method to get at the point estimates of these percentiles in the first place. Okay, so the way this proceeds, we generate a weighted estimate of what's called the cumulative distribution function. Some of you might remember this from statistics courses as well. The idea of a CDF. Okay, so it's telling us what proportion of the overall population falls at or below a certain value on the variable of interest. Okay, that's what the CDF is telling us. So the general function for the CDF, we sum over everybody in the population an indicator variable. Remember, that's what that I means. Okay, so that variable is 1 if that condition is true, 0 otherwise. So if the value on the variable of interest is less than or equal to the chosen value of x, defined in this function, it tells us what proportion of the overall population is at or below that particular value of x on this variable. Okay, and that gives us an idea of the overall distribution of that variable. So that's for the population. Given a probability sample, we can compute a weighted estimator of that CDF that's written as you see here. And this is nothing new, right? This is just a weighted proportion. You guys have seen this formula many, many times now. Okay, so we're just creating an indicator for whether or not that condition holds. Each person's contribution to this weighted estimate is multiplied by their weight. And that gives us a weighted estimate of the proportion at or below that particular value of x. The difference with the CDF, to fully form the CDF, we need to compute that at all possible values of x. That gives us the full cumulative distribution function, rather than just the value of one particular value of x. So once we have that weighted estimate, then we can compute a weighted estimate of that entire cumulative distribution function. And we need this as a first step in forming point estimates of percentiles. That's the key here. We need to have this full CDF before we can compute weighted estimates of the percentiles. Okay, so then the Qth quantile for a variable y is a related concept for that variable y, is the smallest value of the variable such that the estimated CDF is greater than or equal to that value of Q. Okay, so there's a lot going on in that definition. But we can set Q to be 0.25, for example, if we want the first quartile. We can set Q to be 0.5 if we want the median, right? 0.75 if we want the third quartile, 0.95 if we want the 95th percentile. But it's the smallest value of the variable such that the estimated CDF that we just computed is greater than or equal to that particular quantile. Okay, that gives us the Qth quantile. All right, so that's the second piece that we need. Okay, given our descriptive objective, we define the value of Q, okay, that lets us calculate our estimate of interest. All right, so we have our estimated CDF, we have our desired value of Q, and then most of the software by default implements what's called the ungrouped estimation method, given those two important pieces of information. Okay, the ungrouped estimation method starts by ordering all of the values on the variable of interest in your sample from smallest to largest. So this is order statistic notation. That's, you see the parentheses and then the number in the context of the larger overall sample. All of the values are ordered. So x sub 1 in parentheses, that's the smallest value on the variable of interest. And things are sorted all the way up to the largest value on the variable of interest. That's what the lowercase n means for the overall sample. Okay? So you sort the values in the data set by values on the variable of interest, and then you find the value of j in the context of these order statistics. So exactly what observation satisfies this inequality. And notice that the inequality relies on the weighted estimate of the CDF and the selected value of Q. Okay, so those are the input pieces that are needed. So we want to find the value of j that satisfies this particular inequality. So the weighted estimate of the CDF is less or equal to Q, and the weighted estimate of the CDF at the next ordered value is greater than Q. Okay, what is the value that satisfies this particular inequality? That's our beginning point for the weighted estimate of the percentile. Okay. Can't get there, and so we have each of these two pieces to start. Right? So we find the value of j that satisfies that expression. Then there's a slight bias correction that we need to get an unbiased estimate of that weighted percentile. Okay? So we take that value of j from the order statistics. That's like our starting point, like I said. And then we add this really ugly looking term that you see here to compute the overall weighted estimate of that particular percentile for the choice of q. This big ugly thing again is necessary to make sure that this is an unbiased estimate of the overall population quantile. We can't just go with whatever that selected value of j was. We have to add this bias correction, right? That entire calculation gives us our weighted estimate of that particular percentile. But I want you to take a careful look at that bias correction, okay? Again, pretty ugly function. We talked about linearization and how the idea of linearization is that you re-express a complicated nonlinear estimate as a function of weighted totals, okay, using that Taylor series expansion. Think about what's actually going on in this calculation. Remember, the weighted estimate of the CDF is itself a weighted ratio. So this bias correction is like a function of ratios of ratios. It's a mess. So you think about what the Taylor series expansion would look like for this entire estimate. It's very complicated. It actually took an entire paper to arrive at that solution. This paper by David Binder in 1991, he was one of the first to really look at linearized approaches to estimating the variances of these kinds of percentiles. They're not straightforward because this percentile is a step function of the observed data. So what happens in this case is that we can have ties in the data set. Multiple people may have the same value of their PSA score, or they might have the same value of household income, or they might have the same value of blood pressure, right? That means multiple people in the data set satisfy the same percentile on the variable of interest. And what happens is that the resulting function of the observed data looks like a step function because of these ties. If we look at the value of the percentile as a function of the observed variables, it looks something like this, okay? It's not a smooth function. And that's one of the things that folks grappled with when trying to apply linearization to this particular type of weighted estimate, is that you end up with a case where you can't take derivatives at every possible point of that step function. It's not a smooth function. Okay? So Binder had to think about alternatives for how you could apply linearization to try to estimate the variance. Simulation studies in general, comparing the different variance estimation techniques, have suggested that balanced repeated replication or bootstrapping are actually the better approaches for estimating the sampling variance of a weighted estimate of a percentile. So this is honestly one of the only estimates where there is notable differences in performance across the variance estimation methods. And some of the methods do a better job of converging to the true theoretical variance of this estimate. Linearization can break down for the reasons that I just indicated. And jackknifing actually has very poor properties for estimates of percentiles. So if a lot of your descriptive work focuses on estimation of percentiles, it's a good idea to either consider balanced repeated replication or bootstrapping for variance estimation. You'll be okay if you use Binder's linearization technique, maybe jackknifing to some extent, but simulation studies, including the one that I've cited here, which is up on Canvas, have demonstrated that balanced repeated replication and bootstrapping have better properties for weighted estimates of quantiles because of the unique form of this estimator. Okay? So one of the only times in the course that we're going to be saying that there are notable differences demonstrated in the literature between the variance estimation methods for this particular estimate. Okay? So we're going to look at some examples here of what I mean by that coming up. All right, oops. So what software makes this possible? In R, you have the SVY quantile function within the survey package, okay? Truthfully, I use R exclusively for descriptive analyses that involve quantiles. Why? Because Stata users don't have a base command for percentile estimation. Okay? You can calculate weighted point estimates of percentiles, but you can't get the standard errors. Still not entirely clear to me why that is within Stata, even in version 18.5, which is now available. I think it's because of this debate about the best way to compute the standard errors, which I don't think is much of a debate anymore in the literature, but for whatever reason, they haven't proceeded with a survey version of percentile within the base data package. So one of my colleagues, Stas Kolnikov, he actually wrote an add-on command, a user command that calculates weighted estimates of percentiles. And I've included the two commands that you can use here to install and download that user written command within Stata. I'm going to illustrate it here in a second. Okay. But there is no base command. Okay. So in these cases, I like Stas's function, but Lumley has programmed SVY quantile specifically for this purpose. All right. Westfair software also makes balanced repeated replication possible. So you can use that free software as well if you prefer. SAS uses Taylor series linearization by default. So you have to change the variance estimation technique to one of these alternatives or use available replicate weights to estimate the variances. SPSS has the same issue right now as Stata. So again, if you have colleagues using SPSS, SPSS does not have a design adjusted version of the percentile command. Okay, so simple descriptive quantity, but all of these issues in the background make it more difficult to estimate variance. Okay, so some of these packages don't yet have a procedure for this simple type of descriptive estimation. Okay, so definitely something to be aware of. And remember, the simulation studies show that balanced repeated replication works well for quantile estimation, but what do we need in order to implement balanced repeated replication? What kind of sampling error calculation model do we need to implement BRR? 2 clusters per stratum, right? Right. So again, if we're given a sampling error calculation model that has some strata with more than 2 clusters, we say, well, okay, we have to use the jackknife. But then you look at this literature and you say, but the jackknife has very poor properties for percentiles. So then what do we do? Then you have to either think about these linearization approximations or think about some form of bootstrap replicated variance estimation, okay, as alternatives.
Great.
Yep.
SAS has the option to use bootstrap.
It will do that, but remember, it's going to create that for you on the fly, right? So if you do that on the fly, you're not calibrating each of those weights unless you take the steps to do that. So remember, if you're given stratum and cluster codes, you have the option to do that kind of stuff on the fly, but you're not getting the full adjustment that a data producer would otherwise provide. So it's there, but you're not getting the option isn't immediately built in or programmed in to calculate adjustments for each of those replicate weights.
But what is the worst option, using GSL or jackknife?
Jackknife. In the context of the properties of these different methods, jackknife has very poor performance. The jackknife actually converges away from the theoretical variance. So it's not a consistent variance estimator. So of all these options, I would use the linearized approximation well before considering the jackknife. Okay. So let's look at some examples here. So this example here on slide 7 is looking at estimation of percentiles based on total household wealth in the 2012 health and retirement study. Okay. So the goal here is to calculate the first quartile, the median, and the third quartile for the estimation of total household wealth. Okay. Describing the distribution of this variable at the household level. So this is a household level variable in the 2012 HRS. Okay. So what I'm showing here is SAS using the linearized approximation, first of all, that's SAS TSL. Then I'm showing SAS using balanced repeated replication. Why? Because the HRS sampling error calculation model gives me 2 clusters per stratum. it's possible to use BRR in this case because the HRS sampling error calculation model, 2 cluster units per stratum for the sake of variance estimation. If that wasn't the case in HRS, I would not be able to compute that second column of results. Okay. Then I show in Stata that default of using linearization using the user written command. Now, if you have replicate weights in Stata, you can specify those and then obtain these corresponding estimates. I'll tell you how that Stata command works in a second. All right. So first I want to talk about the R function because this is again programming exactly what's in the literature right now. So you would use SVY quantile in the survey package. First argument after a tilde is the continuous variable that you're using to estimate the quantiles of interest. Okay. So that's that total household income variable. Then we have our design object, and that design object needs to reflect the household weights, not the respondent weights, the household weights. Okay. Remember, for our earlier analyses of household level variables in HRS, we needed to look at the subpopulation of individuals who are financial reporters, and we needed to use the household weight. Okay. That's what that sub design object is looking at here, that specific subpopulation. All right. Then the third argument is a vector of the quantiles of interest. Okay. So after specifying the variable, the survey design object, that third argument is a vector of exactly what quantiles you wish to compute. Okay. So in this case, we specify 0.25, 0.5, and 0.75. You can put whatever values there between 0 and 1 that you wanted. Okay, so that's a nice flexibility. And then we're requesting confidence intervals as well for these particular quantiles. All right, so pretty easy command to use, but nice that it's automatically built in here within R. All right. Now in Stata, we have SVY set like we've done before, okay, setting the same design features. But again, we're not using an SVY command. We have to download and install this user written command called EPCtile. Okay. Now, the way that EPCtile works, first variable that you list is the analysis variable of interest. Then after a comma, you submit the option percentiles with integer versions of the percentiles that you want to use. So not decimals like we see within R, which is using the quantile expression. Stata is calling for percentiles in this user written command. Okay, so that's why we're using 25, 50, and 75. Okay, then we indicate the specific subpopulation, right? Okay, so like we had in the subpop option within the base SVY commands, we're adding the subpop option here for this user written command. It just comes after a comma in this user written command. So that's what's important to recognize. And then we add this SVY option to invoke all of the design features that were previously survey set. So the user written command will refer back to whatever design variables were declared globally, and the SVY option invokes those for the purpose of this estimation. Okay, and by default, EPCtile is going to use linearization. Okay, that approximate linearization. So you would need to specify replicate weights within survey set or change the variance estimation to not jackknife, but balanced repeated replication or bootstrapping on the fly, okay, in survey set if you were doing this way. Okay. Okay, so using these different approaches, these are the estimates that would be generated. And again, regardless of the variance estimation method, you should not see any differences in your point estimates based on the ungroup method. So across these different approaches, you see the same weighted point estimates of these percentiles. Okay, the first quartile, the median, and the third quartile. So you can see that first quartile, only about 22,000 for total household assets. Okay, so this is a highly skewed variable, as again is the case with most measures of wealth or financial income. Okay. Third quartile, 440,000 basically. Okay. Look at the difference in terms of this distribution. This is by no means a symmetrical distribution, okay, which is usually the case. So you see then the linearized standard error, and I want you to compare the linearized standard errors here using that approximate method that Binder talked about to the balanced repeated replication standard errors. What do you consistently note between these standard errors using BRR versus using TSL? What's the difference that you see?
BRR is larger.
Right? So what's happening with that Taylor series approximation is you're underestimating. And that's what all the simulation studies have shown. Okay, you're being too liberal using those linearized versions of variance estimation for these particular quantiles. So remember, previous examples, right, that we were looking at, we were talking about differences between the variance estimation methods at like the 5th decimal place. It just looked like the variance estimation method didn't matter. Here, you see a percentage point difference in terms of these standard errors, especially for these higher estimates of the percentiles. So they're not the same in this case. If you have the ability to do BRR, given the sampling error calculation model, definitely a good approach to use. Or you have the ability to create bootstrap replicate weights, good approach to use. TSL is an approximation that may understate your variances slightly. So it's important to recognize that if you're working on these kinds of descriptive estimation tasks. Now, notice in Stata, everything's been rounded, right? That user written command, the default kind of output, everything's going to be rounded to a couple significant digits. That's why it doesn't look exactly equal between linearization here and linearization here, just because Status chose to round everything in this case. You can dig into the actual point estimates with post estimation commands, like I showed previously with looking at totals. But this is the default kind of output that you're going to see as this kind of rounding, which is okay for the purposes of this kind of estimation. We don't need that many significant digits to describe these kinds of quantiles. All right, so this is, again, one of the only cases where there are some notable differences between the variance estimation methods when you're dealing with complex samples. So I just want you to kind of keep that red flag in your mind that if you come across a problem where you have to compute percentiles as part of an analysis project, think about the variance estimation method that you're using and what's possible to compute, okay, given the sampling error calculation model. All right, point estimates aren't the big deal. The variance estimation in this case is really the big deal. Okay, okay. Questions about any of these examples before we move on here? Yep, George.
In terms of using the Taylor series, is there using the
No, yeah, I didn't show the R output here, but you would get the same standard errors. Yep. Where the standard errors are going to vary is when you're using the replication methods.
Question.
If I use TSL option in a summary, for example, I have to put a note saying that the variance is underestimated.
Yeah, so I would add kind of a caveat that says, something to the effect of the sampling error calculation model provided by the data producer had some strata with multiple cluster codes present, something like that, which prevents calculation of BRR replicates. So start off with that kind of caveat. The literature has shown that BRR replicates give you better estimates of variance for these quantiles. We could not do that in this case, so we used a linearized approximation, which has been shown to understate the standard error slightly. Okay, so then that you're kind of starting with that caveat that says, I'm acknowledging that my standard errors may be understated and that my inferences might be overly liberal, right? So if you had like a confidence interval that was right on the range of your hypothesized value, that's where there could be some concern about this.
Question.
Professor, we saw in the previous lectures that bootstrap adjusting for the non-response and bootstrap adjusting for the non-response after yields little difference.
Right.
Is that also the case here?
Yeah, so this is where, again, like I was saying with Glaston, like you don't have the luxury of applying those adjustments if you create those bootstrap replicate weights on the fly. But for the most part, I haven't seen that many big differences, even with quantiles, in terms of adding those additional adjustments each time through. But it doesn't mean it's not worth considering. So if you're a data producer or you're collaborating with a data producer and you want to explore the difference, it's worthwhile to look at just kind of the raw bootstrap replicate weights and see how the variance estimates would compare when using calibrated bootstrap replicate weights and see if it makes a difference for your inference. More than likely it won't, but it's still worth considering. Yep. Especially if those calibration adjustments are crucial, right, for adjusting for bias. Yep. Isaac, yep.
I have a question, like by using the PC tile or external part, we can get the same results.
Yeah, great question. So in Stata, you can get point estimates by using PC tile with a P weight. What you're not going to get are the standard errors. So if all you want to do is calculate and compute point estimates of percentiles, you can use PC tile, no problem. It's actually underscore PC tile, but that's the command that you could use. But there's no survey version of that. So all you're going to get from that are the weighted point estimates. If you want to make inference about these percentiles, that approach would not allow you to do so, right? Because you're not going to get the standard errors. That's what's provided with base data is PC tile, where you can add a P weight in square brackets, but that's just going to give you point estimates.
Question?
Yeah, Sophia, yep.
Yes, I have encountered a scenario before which I run a median using EPC tile instead of,
Yep.
and do you mind to elaborate on the asymmetric confidence interval part? Because I have other statisticians run the same median, but they have symmetric confidence
Right.
interval in SAS and Sudan.
Right. So when you form confidence intervals for percentiles, that's similar to what we talked about with confidence intervals for proportions. Remember, where there are different types of intervals that you can compute, and they vary in terms of their coverage. So there are different types of intervals that you can also compute for percentiles using different methods. Like a previous slide mentioned Woodruff's method. Like that's one way of forming intervals for these kinds of weighted percentiles, where those symmetric intervals may not necessarily have good coverage. Same issue that we came across with proportions. So there are different flavors of confidence intervals that the different software will compute by default. And you can read a little bit more in the documentation about what those are. But there's no guarantee if you're not using that walled approach that you're going to get a symmetric interval. And that is the case with EPC tile. I don't remember exactly what flavor of confidence interval that EPC tile uses by default, but it does not yield symmetric intervals. So it's not unusual that you would see that for these kinds of estimates.
Thank you.
Okay, other questions on this example? Other questions? Okay, so we're not going to have a homework exercise focused on percentiles. Okay, so if you need to do this for your job or your research projects or anything else, good idea to practice when you get the chance using EPC tile, using SVY quantile. Just take a shot at doing this with a couple continuous variables just to get the idea down of what you're seeing. So, okay, good. Next, so we've been talking about subpopulation analysis kind of the whole way so far in the class when we've been going through descriptive examples. And this is just, again, at this point, going to be a reiteration of many of these important points about subpopulation analysis and how to do that appropriately, especially when you're using linearization. Okay, so examples of subpopulations. Again, we've kind of been talking about this the whole time, but I would say rarely does an analysis of a complex sample survey data set focus on the entire sample all at once. People are always going to be interested in different subpopulations, different subclasses, focusing on specific groups that were sampled as part of that larger data collection. Okay, so very common that this is done. So you might be focused on men, women, non-binary individuals, age groups, sexual identity groups, disease groups like people who suffer from a particular condition like asthma, people who voted, people who didn't vote, homeowners versus renters, people with different income brackets, people with different education brackets. All of these are examples of different types of subpopulation analysis. And like I said, it's arguably more common that people are breaking estimates down by these different subgroups than just looking at full sample estimates exclusively. So it's very important to be careful about when you're doing these kinds of subpopulation analysis. So I've alluded to, as we've looked at examples, this difference between unconditional and conditional approaches to subpopulation analysis. And this book by Cochrane, the sampling techniques book, was really the first to really dive into this distinction between how you can perform these kinds of analyses. Steve, Pat, and I looked at it in a little bit more detail in this 2008 paper here that was in the Data Journal, actually. The conditional approach to this kind of analysis conditions on the observed subpopulation sizes as though they were fixed. So if you happen to see a subsample of 1,322 women, the analysis approach, if you delete everybody else that you don't care about, assumes that every single hypothetical repeated sample is going to give you 1,322 women. And as we know, unless gender is part of the stratification, that's not going to be the case. That would only be the case when that subgroup sample size is fixed if the subgroup was defined entirely by the stratified design. Okay, right? Because the amount of sample allocated to the different strata, that's not going to change across hypothetical repeated samples. If gender was not part of the stratification, in my little example here, one sample I might get 1,322 women. Next sample I might get 1,544. Next sample I might get 927. It's a random variable. And when you take the conditional analysis approach, the variability in that subgroup sample size is not taken into account. That's the key theoretical difference here. That is treated like a stratified sample size that is fixed by design, when in many cases, that's simply not the case. Okay, that sample size is going to vary from one hypothetical probability sample to the next. Okay, and unfortunately, that happens for variance estimation when you use commands in the software procedures like if, or by, or where, to physically delete the cases that you don't care about, that don't belong to your subpopulation. That automatically invokes this kind of conditional approach to the overall analysis. Okay, and that's what we want to avoid when doing these kinds of analysis, because that can lead to variance estimates that are too small, that don't reflect the additional variability in the size of your subpopulation sample. Okay, so conditional analysis is only okay in a couple of scenarios. Again, where the subgroup is entirely defined by the stratified design, or you have a simple random sample. Okay, there you're not really going to lose a lot in terms of doing this kind of conditional analysis. Again, it doesn't work generally for stratified samples because the distribution of your subpopulation cases across the different strata is a random variable. Again, it's rarely fixed by design, and we want to take that variability into account. Okay. All right, so that's the key kind of distinguishing factor here. The unconditional approach to this kind of subpopulation analysis treats the stratum subpopulation sizes as though they are random variables, which is the appropriate approach. Okay? And even if they are fixed, you're still not going to lose anything. Okay? That's the key point about this, is that you can never really go wrong with the unconditional approach. Okay? So if you get into the habit of using this approach in all of your subpopulation analyses, you're never going to go wrong with these kinds of analyses. Okay? So what this does is it recognizes the variability, the sampling variability in the size of your subpopulation across the strata, and it includes those sampling zeros. Okay? Those cases where by random chance, you didn't happen to have any sample coming from a stratum or coming from a cluster. Okay? When in theory you could have. That's the thing to recognize. That's the case where if we were to physically delete the cases we don't care about, all those sample design features with sampling zeros, those strata, those clusters, where there just so happen not to be anybody in your subpopulation of the sample, they get deleted. In the unconditional approach, the procedure reads the entire data set, recognizes the sampling zeros, and accounts for those in the variance estimation. Right? So if I have a stratum where one cluster has a sampling zero for my subpopulation of interest, remember for linearization, we're looking at between cluster variance and the totals. One of those clusters contributes a total of 0. to that variance estimation, and that is the valid approach. It recognizes that variability, the fact that we just so happen to have a sampling zero in that one cluster, okay? Rather than deleting that cluster entirely, which is what the conditional approach does. So we recognize the variability in that sample size. So as we've talked about in previous examples, the Stata subpop option that we've seen numerous times now, the subset or the survey by functions within R, they all implement this unconditional approach. Okay, and these ensure that this kind of variability in the subpopulation sample sizes is reflected in the standard errors of your estimates. And that's what we dug into in that 2008 paper a little bit more. Where exactly is that being accounted for in the variance estimates? Okay, to demonstrate that the unconditional approach is important for doing that. Because remember, with linearization, some software like Stata will default to just shutting down if you don't have multiple clusters within a given stratum. And this is almost 100% of the time the reason why that's happening. Yep, George?
Brady, is that the reason why you recommended that you don't
Exactly.
just
Yep.
process the
Exactly, right? So there's a couple different ways you could delete cases. Like one is when you're actually running the analysis and running the procedure, you use these keywords like if or by or where. So you condition your analysis on a particular subpopulation without using these appropriate subpop commands. That's one way to do it kind of on the fly. Another way that's probably more common is when you're working with the data originally and you're doing data management, you have a step in there that says delete all the cases that are met, or delete all the cases that don't satisfy my subpopulation criteria. That's arguably the more common case, how this happens. And then when you do that, right, you may be your reduced data set, you may have some strata that only have one cluster or something like that. So when you supply that reduced data set to the software, not only are you at risk of treating the sample size like it's fixed, but you're at risk of this case if you're using linearization where you have some strata with only one cluster code. So there's all kinds of issues that can emerge if you're in that habit of physically deleting the cases that you don't care about, whether it's on the fly or whether it's when you're managing the data. Okay, so best habits, best practices when you're working with these kinds of data sets, just keep the full sample for everything that you do. Okay, like we talked about in chapter 4, if you're going to be doing a lot of subpopulation work, just create indicators for those subpopulations when you're first managing the data. Never delete the cases that you don't care about. Okay? It avoids all these problems. Okay. Okay, other questions so far on the idea here? Isaac, yep.
So for the unconditional analysis, we need to delete our responses and missing it.
They will be dropped. So that's a good question, Isaac. So the software will be dropping cases with missing data on a variable of interest. So this is interesting. A while ago, Stata was initially treating, like, what's the best way to say this? They were processing missing data first and then looking at the subpopulation. So even if you weren't deleting cases like I just talked about, if there were missing values, the procedures would delete those cases with missing values anyway. Okay? And Stata people who were aware of this issue, Stata users, started complaining and saying, well, like, you know, we understand the unconditional approach, but the procedures are killing the missing data first, which leads to the same problem as deleting cases. So a while back, Stata changed the way that the subpop option was working in the background to read the entire sample first, understand the sampling zeros, and then delete the missing values. They were doing it the other way first, and then too many people complained, then they changed it, and now it processes the entire data set first before handling the missing data. Okay? But it still doesn't avoid the need to think about how to handle those missing values on your own, right? You might impute them. You know, it doesn't make sense to throw those cases out. Those are all questions that you need to think about before you jump into the analysis. But these approaches assume that you have complete data, right? You just have to think about how the missing cases are being handled by the software. So what some people will do is they will define a subpopulation indicator to be, you have to belong to the subpopulation of interest and you have to have valid values. So that way you have a 1 for all the people with complete data and belonging to the subpopulation of interest. And you have a 0 for everybody else or the cases that have missing data. Just guarantees that they get processed, even though they have missing values. So that's one way around that. Yep. Another way around that, where you can kind of trick the software, is create that indicator variable, okay? And if there are missing values on the cases that have zeros, right? Because you've defined that having a missing value is not belonging to your subpopulation. If other software is still dropping them first, like they haven't made that change that's stated that I just talked about, like they're just being deleted first and foremost, just create a copy of the analysis variable and just plug in random plausible values for those cases with missing data. Not any kind of scientific imputation, but as long as they have a 0 on your subpopulation indicator, just code in a constant value or something. All that's going to do is prevent those cases from being dropped. You're still analyzing the subpopulation that you care about because you have that 1, 0 variable. You're just preventing those cases from being deleted by the software. They're still not going to get analyzed as long as you do the subpop analysis correctly, but at least they're not going to get dropped. So you can create a copy of your analysis variable, just fill in those missing values because they're going to get ignored anyway because there's zeros on your subpop indicator, and then proceed with your analyses of that new variable that you created. That's another way around it. Okay, other questions so far on this idea, these concepts here? Okay, so as I've mentioned, the incorrect conditional approach can result in the case where there's only one sampling area computation unit detected within particular strata, and that can prevent appropriate variance estimation. But different software reacts to this differently. This is also very important to recognize. Remember, Stata had that single unit option in survey set, which defaults to missing. So if you see a stratum that only has a single cluster code present, don't compute standard errors or confidence intervals, okay? But there are other ways around that, other options there that are like ad hoc for computing variance estimates. SAS, the survey procedures in SAS, just remove that stratum from the analysis altogether. It doesn't stop and give you a missing standard error. It literally assumes that that stratum is not contributing anything to the variance estimation, which is very odd to me that they've selected that by default. Furthermore, SAS, when it runs into this problem, does not throw an error message. It throws a note. Those of you who are SAS users, it's a blue note in the log that says, oh, hi, hey, you have a stratum that only has a single sampling error code, and I'm going to ignore it for variance estimation. That should be an error. It should not be a note because many SAS users just ignore the log. And that's the only place that you see it. Okay? So SAS is taking the approach that if I find a stratum that only has a single cluster present, I'm just going to ignore it. Rather than Stata, which is saying, I'm not going to give you a standard error, period, because you haven't given me enough information. Okay? So the easiest way around all of these problems is just to use the right subpop options in a different software. Okay? In fact, another thing that's especially weird that SAS does, if you say if or by or where to subset your analyses to a particular subgroup, SAS gives you like a paragraph long note in the log that basically slaps you on the wrist. It says, hey, you're not doing this correctly. You should really be using the domain keyword. What this can lead to is underestimates of variance, blah, 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 blah. This entire thing is just a note. It should be an error. But that's not how SAS is operating. Again, if you're not in the habit of checking your SAS log, you're not going to see this. It literally just says, use domain to do subpopulation analyses, but it's not stopping you from interpreting the output. Okay? So all you have to do to get around that problem is use the domain keyword within SAS. Very simple fixes for all these issues, for sure. Okay, so as we've talked about, to correctly implement the unconditional analysis, you can use over as an option in Stata, and that will repeat unconditional analyses for all possible groups of some subgroup variable in the data set. We've seen examples of that. Okay. Or you can use subpop, where subpop is available for pretty much every SVY command in Stata. Okay, you're going to see it for all the SVY commands. You're only going to see over for the descriptive analysis commands in Stata. You're not going to see it for the regression commands that we're going to start talking about next week. You only see subpop for every command, right? But each of these are equally valid ways to implement the unconditional analyses when you're doing subpop analyses, okay? Okay, so again, you're always going to get the correct result by simply using subpop in Stata. If you just get into that habit of creating dummy variables for your subpop and then using subpop, you're always going to be fine. Okay, so it's a simple fix. Then the same is true when using subset or SVY by within ARM. We've seen this in earlier examples, how to use these two functions to implement these kinds of unconditional analyses correctly. Okay. Now, another case where the software differs, in Stata, if Stata finds that there's an entire stratum with 0 cases, Stata assumes that that stratum is not contributing any degrees of freedom. Because Stata is making the assumption that if an entire stratum doesn't include your subpop, no repeated samples are ever going to include that subpop coming from that stratum. Okay, so if an entire stratum is a sampling 0, Stata removes it from the degrees of freedom calculations. And you'll get an explicit note about this in the output, that Stata is kicking out certain strata that had no subpopulation elements present. Okay, that's different from what SAS is doing. SAS is using fixed degrees of freedom. So if you input 32 degrees of freedom, SAS is using 32 degrees of freedom for your confidence intervals. It doesn't matter if there are some strata that have sampling zeros. Stata is using this more variable degrees of freedom calculation. And you can make arguments one way or the other, but those are also different approaches to be aware of, like when you're reporting test statistics and so forth. Okay, so let's look at an example and then we'll take a break here. This is looking at estimation of mean household assets by different levels of education in the health and retirement study. So a researcher might be setting out to see if your mean total household assets vary depending on how much education you've received. Okay, as a study of kind of socioeconomic status, right? So in the HRS, we're first creating our subpop indicator. That's the practice that you want to get into. First things first, when you're managing the data, create a 1-0 variable that indicates who's in your subpopulation and who's not. Okay, the best habit to get into, right? So I'm making an indicator for financial reporters who are providing information about the household, not about the individual respondents. Okay, then I set my HRS design features, choosing the household weight because this is a household level measure and I want to calculate a household level estimate. Okay, so my weight that I choose is NWGTHH instead of NWGTR, which would be for respondent level variables. Cluster codes, stratum codes. Okay. Then in the actual analysis command, I say SVY, and then I add that subpop option where since I already have the dummy variable in the data set, I can just refer to that dummy variable in subpop. Alternatively, I could have used that condition inside the parentheses for subpop to implement the unconditional approach. The key thing is that I'm not saying if as a part of that command. I'm implementing the unconditional approach. So I want that to be my subpopulation unconditionally. I want the mean of that household asset, total household asset variable. That's the name of the variable in the HRS data set. In addition, I want unconditional subpop analyses for each possible level of education category. So this is a way of specifying both financial reporters and repeating the analysis unconditionally for all the possible categories of education. Everybody with me with what the syntax is doing? So I'm combining these two unconditional commands, perfectly fine to do that. All right, so what I see in the output for each level of education, all 4 categories here, which Stata labels in the output, I see the weighted estimate of the mean, I see the linearized standard error, and I see the 95% confidence interval for that particular subgroup. And if I look at these intervals, again, just informally to see if they overlap, I see no evidence of overlap whatsoever among these four groups. So again, leading into our discussion later today of these formal tests of differences between subgroups, just glancing at these 95% confidence intervals, I don't see any evidence at all that these groups are similar to each other. So there are stark differences in terms of mean total household assets between these four different education categories, where there's essentially a curvilinear relationship in terms of the mean total household assets as a function of education. Okay, so we see that right away. Important thing, these are all unconditional variance estimates that fully reflect the variability of the subpopulation sample size of financial reporters and people with different levels of education. None of this was part of the HRS stratification. Okay, so there's no justification whatsoever to treat this conditionally. These are all, these subpop sample sizes are all random variables. Okay, that's why we're treating this unconditionally. So we're going to use this output later on for t-tests, informal comparisons, pairwise comparisons of these different groups like you do in an ANOVA or something like that. That's what we're going to talk about next. Yep, George?
Can you explain, so the variable that you are generating, that you are assigning once.
Yep.
It's a new variable in the
Right.
data set. And then, so you're not using, I'm a bit confused. So you're not using any existing, something completely new that you are, it's not related to anything else in the.
Well, it is. It's a function of K-FINR. The problem was that K-FINR was coded 1 and 2.
Oh.
I need a 1, 0 variable, right? So I'm starting by setting that new variable equal to 1. Then for those people who are not equal to 1 on K-FINR, they get a 0. If I was to input a variable taking values 1 and 2 to the subpop command, Stata would throw an error. Okay, that has to be a 1, 0 variable. 1 people in the subpop, 0 people not in the subpop. Okay. Other questions about this example here? Okay, let's just look at the R code and then we'll take a break. So in R, to implement the unconditional approach like we have talked about previously, I can use survey by. Okay, so SVY by is saying for that analysis variable after a tilde, I want separate analyses for each category of education, EdCat, that's the second argument. The third argument is a survey design object that has been subset to financial reporters. That's the HRS SVY sub. So I'm not showing that subset function, but we've seen that in previous code. Fourth argument is the analysis function to actually use. So I want to calculate the mean. Fifth argument, I'm removing missing values. Okay, that's again like Isaac's question. We have to be careful about how many people have missing values in that case. Then, given the object that I've created here, I can just look at the estimates and standard errors and then compute confidence intervals for those estimates for each of the different subgroups. Okay. So that's the analogous R code to do what we were doing in Stata. Key things here, use the subset function to create the appropriate subset of your survey design object, which handles this unconditionally, and then repeating the analysis for the different categories of EdCat as the second argument. Okay. Everybody with me on that code? So again, solutions, very easy. You just have to use the right option, use the right function to implement the unconditional approach. You can never go wrong, even if you have where a conditional analysis would be appropriate. Even if you have a subpop defined entirely by a stratum, you'll still get the right answer if you're using subpop. There's no reason whatsoever not to just use that every time. Okay, that's the message here. Okay, good. It's about 10:12, so why don't we take a break till about 10:20. And then we're going to get into, once you've done these descriptive analyses for different subgroups, how do you go about comparing the parameters for different subgroups? Like if we want to do a t-test or multiple pairwise comparisons, how do we go about doing that? How do we work with functions of estimates in this context? Okay, so that's our last topic for today. Okay, so we'll break till about 10:20 and then I'll start back up. Okay, thank you.
Yeah, I know. I don't know what it is.
It's true. Like, true.
It's useful.
Yeah.
Oh.
Yeah, but yes, I will just.
He does it all the time.
I was doing the same. So we have just dealing with the subpopulation, that is the variable in the data set. And so this is my. So I am just going to have complete cases and analysis. So this is my subpopulation for the children of 5%. So yeah, if I'm this command, I am going to have subpopulation like this whole
Yeah.
variable,
Yeah.
and then I am getting.
But see what it's
yeah.
saying though? So it's saying that the variable that you're inputting is not a 1, 0 variable. So it's making the assumption that everything not equal to 0 indicates your subpopulation. So what that means is that people with a 1, 2, 3, 4, 5, anything not 0, they're being included. So if all you care about is that first category, you gotta recode that variable into a 1 for that first category and a 0 for the other. That's exactly the problem, is that it's treating everything not zero.
I want you just anymore.
So here I'm having the complete data set, but for the subpopulation, it's having the complete information.
Exactly.
Ignoring the missing.
That's the problem.
But when I matched my result with my report, the survey, so I'm getting the same results as
Okay.
yeah. So it is it doesn't have any impact to my result, but as you were instructing us that we need to make it binary first, and then we need to
Yeah.
apply. the
So
population
that would just be my question. Is that, like, if you go back to that tabulation that you were just showing me? No, the tab that you just run, if you run that tab with no label. So go back to Stata and then just say tab, or just recall that same command. And then just add the no label option.
So I will say.
Right, so basically, every single case, because none of these are 0, every single case, save the missing data that's being thrown out, is treated as your subpopulation. If that's true, and these are all children, you're fine.
Yeah, these are all children's results. Basically, now what we are having, I am having just the students with the completed questionnaire,
Okay.
completed interview.
Yep.
So this is like going to have final.
Okay.
Overall, we have 37.
Yeah.
But right now, I'm dealing with the 30.
All I'm saying is this is very dangerous.
Yeah.
I would get out of this habit.
Yeah.
Because if you're using like another grouping variable for some different subpopulation, where there are no zeros again, and you don't mean to analyze all these 2 through 6s, like in this case, they're being dropped, right? But if for another analysis, these were not dropped, you're mistakenly coding your subpopulation as including all these individuals. So even though you're getting the same results, I would still recode this to 1, 0, just to get into that habit.
On the safe side. And one thing, sir, can you please guide us how to install the EPs?
Yeah, so say find it, EP set, I'm assuming you're connected to the internet, yeah, so say find it
From the command.
just the command, just like the command. Find it. And then EPC town. And then that'll take you to the appropriate link. So just click on one of those links. I don't think there's a difference. And then it'll say like, click here to install. So this is actually installing the code to run that command. So now it says installation is complete. So now you can type, for example, go back to your command window. Now you can type help EPC time. Help, not Joe.
Yes, I understand. Especially you guys, that is what you see.
And you'll see that.
Yeah, thank you, sir. We start doing what usually one, so we will be able to, yeah. So I think from today, I think so from today, you need to start working. Yeah, so many, so that's. No, I don't need this. For example, this one. The eating is. It works. Then you will. Keep in touch, yeah. Yeah, you.
I need a flower.
She's, what? Yeah, I did. What is that? Extra mark.
Okay. All right, let's start back up again here. So far today, we've talked about percentile estimation and subpopulation analysis. I want to reiterate an important point about variance estimation method. Everything we just talked about, unconditional versus conditional, remember that that only applies to linearization. Okay, everything we just talked about, because the issues again were the subpopulation sample sizes within the different strata, within the different clusters, because all those clusters, that's what's contributing to the variance estimation. We're looking at between cluster variability in totals. So we need to know what those cluster codes are. We need their sample sizes. Okay. If you're using jackknife or balanced repeated replication or bootstrapping, stratum and cluster codes are irrelevant, right? All that's being used for variance estimation are the point estimates from those replicate weights. So while it's still a good habit to use subpop every time that you're running one of these commands or survey by or whatever it is, it's technically not necessary if you're using a replication method. Okay? So you can get by without worrying about subpop and using replication with a conditional approach. I would not recommend it, okay? But you'd still be safe, given that conceptual difference. Best practice, just get into the habit of specifying those subpopulation indicator variables every time, even if you're using replication, okay? It's not gonna hurt anything. Just get into that habit of doing that unconditional analysis. But remember, this really applies to linearization, not replication techniques. Okay, everybody clear on that distinction here? Okay, so we now have estimates for different subgroups based on that kind of unconditional approach. And suppose that we want to combine those estimates in some way. Maybe we want to add two estimates together, or we're creating some kind of socioeconomic status index where there's a weighted function of estimates on different variables, or we want to look at the difference in two estimates. We're interested in some general combination of the subgroup estimates that we've computed, okay? So take a look at this formula here. This is a general property of taking variances of linear combinations. And we've already talked about this in the context of linearization, okay? So let J, little j, denote different subgroups that we're interested in, okay? And let theta hat denote the estimate of interest for subgroup J, okay? We are interested in making inference about some linear combination or some function of those subgroup estimates, where this a sub j is a constant that could take on a different value for each estimate that we're combining, okay? So in the very simplest case, a sub j might be 1 for one particular subgroup, and then -1 for another subgroup. That would set up a comparison of those means. The combination of interest is just the difference of those two estimates. Okay? We could think of any general combination that we wanted, but people often ask the question, well, where's my survey t-test? Where's SVY:t-test? It doesn't exist in any of the packages, because you need to use this more general framework for calculating or for making inferences about functions of estimates. Okay, so we would frame a t-test as a difference between two estimates in this more general framework. Okay, so if that quantity inside parentheses is our combination of interest, our linear combination, this is the full expression for the variance of that combination of interest. Okay, we have that, we square those constants, multiply by the variance of our estimates, and sum those across all the different subgroups we're combining. Then we have to worry about those covariances as well. We have to worry about the covariance of the two estimates or the multiple estimates involved in the combination. So that's that additional piece that you see in that overall variance expression. All right, so we get this from linearization or replication or whatever variance estimation technique we use. We also get these covariances. So all this stuff's already been computed. This formula is easy to process given estimates from a prior analysis. We just need to use this formula for these general combinations of estimates. So again, back to the example where we're interested in the difference between two means from different subgroups. That's our combination, 1 times the first mean plus -1 times the second mean. Okay? That's our combination of interest. The variance of that combination would be the variance of the first mean plus the variance of the second mean minus twice the covariance of the two means. We got to remember that covariance piece. 2 times 1 times -1. That's where that second piece comes from. All right. So in the background, we're going to show how to use particular functions that combine multiple estimates that have been saved in the software's memory using arbitrary constants to set up whatever combination we want. But in the background, that's the variance calculation that's occurring. Okay. And the inputs to that variance have already accounted for the sample design if you've done the analysis correctly. Those variances and those covariances are already based on linearization or replication or one of these other techniques that we've talked about. Okay, everybody with me so far here? So we can set up whatever combination we want. This is just an example of the combination being a difference in two estimates, if that's our goal. We want to make inference about that difference, so we need the variance of that difference. Okay, so sampling errors for statistics that are functions like we just saw, therefore need computations of variances and covariances. When you're doing subgroup estimation, like using over or survey by or something like that, you don't actually see the covariances in the output. All you see are the variances of the individual subgroup estimates. But rest assured that those covariances are also being computed at the same time. They're just not shown as part of the output when you do this kind of subgroup analysis. So they're saved by the software in a variance covariance matrix that you don't actually see as part of the output, but we can still refer to it for these computations. Okay. Now, in complex sample designs, even though you might have mutually exclusive subgroups, like males and females, for example, there could still be a covariance between those estimates. Okay. Not coming from the fact that you have the same people in both groups, but coming from the fact that you could have people from each of the subgroups in the same cluster. That's what gives rise to the fact that those estimates might be correlated. If you're comparing, for example, males and females, a given sampling error cluster is going to include both males and females. And they're going to be correlated because they're coming from the same cluster. That's what can introduce the covariance in these estimates that we need to account for. And if you look back at that formula, especially for a t-test or a difference in means, the covariance helps us, right? We're subtracting twice the covariance. So if we were to assume that those two estimates were independent of each other, that variance is going to be larger than it should be. So if there's a covariance between those estimates, we want to account for it in that overall variance calculation. And in complex sample designs, it arises from the cluster sampling. Okay. When will the covariance be zero? If, for example, your subgroups are defined by distinct design strata, right? So if you were comparing, say, the Northeast US versus the South US, where there's no overlapping clusters, everything's completely independent, that's where you're going to see a zero covariance. Okay? But if your subgroups can always come from the same sampling cluster, there's more than likely going to be a covariance in those estimates. Okay? So that all gets saved in the background. So you do get linearized covariances, you do get jackknife covariances, bootstrap covariances. Those are all part of the variance estimation. You just don't see it in the output. Those covariances are being computed as well. All right, so let's look at another example here. This is just a case of comparing two groups in terms of means on a particular variable. So this is the number of activities of daily living that require assistance. This is a common variable that's measured in older populations, studies of health. That's our variable of interest. And let's suppose that our analysis objective was to compare these two groups defined by arthritis status. Do you have arthritis or do you not have arthritis? In terms of the number of activities of daily living that require assistance. Okay? So literally, again, like a t-test, comparing people with arthritis to people without arthritis in terms of means on this particular variable. How many activities of daily living require assistance? Okay? This is what the general command would look like, okay, to do that analysis where, again, we're using over to unconditionally compute means for each of those two categories. Arthritis 1 means yes, arthritis 2 means no. So if I glance at these weighted means, it looks like people with arthritis, group 1, have a higher mean than people without arthritis, which is group 2. Okay, people with arthritis are approaching one activity of daily living that they need assistance with on average, okay, as opposed to people without arthritis. You see the linearized standard errors, you see the 95% confidence intervals. Again, if we just glance at those 95% confidence intervals informally, looks like there's a big difference. But we want to show that formally using the procedure that we're talking about right now. Okay? So that's what we've talked about so far. Now we want to go to that next step, look at the variability of that difference in the estimates, and then make inference about that difference. Okay? That's our do the t-test formally, if you will. Okay. Now, remember, in the background, when you do this kind of subgroup analysis, the covariance of those two estimates is also being computed using linearization. We just don't see it in the output. Right? All right. So in Stata, We're going to see how to do this in R as well. In Stata, this is how we do that post-estimation subgroup comparison after we've already run that analysis command. Okay, it's not going to be an option that's part of the analysis command. We have to work with a function of the saved estimates after we've executed the analysis command. Okay, that's how this approach works in all the different software. Okay, first we do the actual descriptive analysis, then we look at a combination of the saved estimates and make inference about that combination. Okay, in this case, we're specifically interested in the difference in means between these two arthritis groups. Okay, there's a very kind of funky notation that newer versions of Stata use to refer to those saved means in memory. Okay, that's what's happening here. So after we run this command on the previous slide, we then execute this post-estimation command. C.numADL refers to the continuous measure of numADL that we just analyzed. That's what the C corresponds to. And then the at means extract the mean for that particular arthritis group, one arthritis. So the arthritis group with a value of 1 on that variable, extract the mean, including its standard error and its covariance with any other means that are listed after this point. Okay? Then we're taking that mean and we're subtracting the mean for arthritis group 2. So same notation for C.numADL, but then we say at 2.arthritis. That refers to that second arthritis group. If we had 4 groups, for example, we only had 2 in this case, but if we had 4, we could say minus C.numADL at 4.arthritis if we want to compare group 1 to group 4. Okay, so that number dot refers to the specific group by value on that grouping variable that was used in your over analysis. And here we just have the 2 groups. We need the C because that's referring to the continuous measure of numADL that was being analyzed here. Okay, so what Stata is going to do with that notation, it's going to extract those point estimates of the means, it's going to extract their variances, and it's going to extract their covariance from the working memory, and then calculate the variance of that linear combination. That's the name of the command, lincom, linear combination. Give me the linear combination of these 2 quantities in addition to its variance and a 95% confidence interval for that linear combination. So it's a question that often comes up, well, why isn't it called SVY lincom? Because it's drawing the SVY estimates from memory. It's drawing all the stuff that's already been computed from memory and then giving us the variance of that linear combination. We don't need the SVY lincom. We're just pulling what we just computed from memory. Okay? So when we do that, it will actually, Stata actually prints kind of the null hypothesis, if you will, that the mean here minus the mean here is equal to 0. Okay? So it kind of prints that for you just to show you that's the linear combination. That's what we're really kind of testing here. All right, so what does the output say? First of all, it shows what it calls the coefficient. That coefficient is the actual weighted point estimate of that quantity, that linear function. So that 0.554, that's just the difference in the 2 estimates from the previous slide. Okay, so that's the weighted estimate of the quantity, the function that you want to form. Okay. Then you have the linearized standard error of that particular estimate. And that's the standard error that accounts for the variances and the covariance of those 2 estimates. So again, the design adjustments are being built into that standard error, even though it's not called a linearized standard error. It's taking the linearized standard error and the covariance from memory to calculate that quantity. Then you see a t statistic, which is just a ratio of the coefficient to its standard error. You see a p-value for that t statistic, and you see a 95% confidence interval for the difference. So looking at that 95% confidence interval, if our null hypothesis is that the difference in means is 0, that 95% confidence interval does not include 0 as a plausible value. We have sufficient evidence to reject that null hypothesis that the difference in means is 0. Okay? This is your survey t-test. Okay? You're not going to see a command to do it. We have to frame it in this general paradigm of functions, of estimates that we've already computed. And we can use this general approach for any type of combination of estimates that we can dream of. That's the nice thing about it. And those covariances will always be accounted for in that kind of calculation. So lincom is a very, very useful general purpose command for combining any types of estimates that have been computed using a design-based command within Stata. Okay, so we're going to come back to that. Now, oh, yep, Jones, yeah.
That's what I find out. Does it matter variable that linear combination, which one comes first? So when
Yes.
you use it,
It does matter. So if I had called this C dot numadl at 2 minus C dot numadl at 1, I would just flip the sign here. I get the same general result, but the point estimate of my difference would be in a different direction. That's all. So it does matter. It's literally computing that combination of estimates, depending on how you specify it. So if you were writing your paper and you wanted to say, I'm comparing people with arthritis to people without arthritis, if there was a positive difference, that would imply that people with arthritis have a higher mean, right? If you say that you're comparing people with arthritis to people without arthritis, and then you report a negative difference, that's going to tell the reader that people without arthritis have the higher mean, which is misleading, right? So this combination that you write out here should match the interpretation that you want to make about your comparison. It does matter the order that they're in. It's not going to matter for the interval in your conclusion. We have to be careful about the nature of the point estimate. I thought I saw another hand.
Can we compare more than?
Yep. So for example, there's all kinds of funky economic indices that could be computed where you're literally taking estimates from like 5 different variables and you're weighting them differentially. You could do that here. Like you could say, I want limcom to be 0.5 times this estimate, plus 0.3 times this estimate, so forth and so on. And it would recognize those coefficients. So yeah, you could have multiple groups, you could have multiple estimates. It just depends on what kind of analysis you just ran. We'll see. Here it's just giving you the confidence interval for this particular combination. That's it. Yep. So you only have a t-test, which is kind of, I don't know, it shows it, but it's not really helpful in this case. What you really want to focus on is the 95% confidence interval. Yep. In the general design-based framework. Yep. Yeah, is right.
But since if we have many clusters, for example, so in this case, if we can consider it as I don't know what, not clusters, I mean.
Right. So Isra's question, if you didn't hear, can we think, is there a way to do an ANOVA if we have more than 2 groups? We're going to talk about that next week when we get to regression. So we're going to talk about computing F-tests like that give us an overall comparison of means across multiple groups in the context of fitting a regression model. We're not there yet. This is just a way to get a confidence interval for an arbitrary function of estimates. So no F-test yet. Yeah, we'll get to that next week. Other questions so far about this example? Yep, we're good.
Said that sometimes the covariances can be affected by the cluster.
Right. Right.
Is there a way that can I control for the cluster so that you know that variance is distinct the 2 subpopulations that you have?
Yeah, that's actually the next slide I was going to show, right? So this next slide, something cool you can do in Stata, after you've done the subgroup analysis and lincom or whatever you've used, you can type the command estat-vce. This will actually show you that variance covariance matrix of the estimates. So this is showing you what the covariance of those 2 estimates was that was adjusting for the cluster sampling. This is where you can actually see that covariance of the 2 estimates. So you could use this information and do your own calculation of that exact same standard error that's shown on the previous slide. This is the stuff that's saved in memory, and you can ensure that you're adjusting for this covariance when you calculate that standard error. And again, that non-zero covariance that we see here is coming from the cluster sampling. Because otherwise, the people with arthritis and people without arthritis, those are distinct groups. They're mutually exclusive. There's no overlap. So the positive covariance of the two estimates that you see here is coming from somewhere else. And in this case, it's coming from the cluster sample. So you can actually see the values of those variances and covariances within Stata by using this post-estimation command. Remember, we've talked about E-stat effects and E-stat size. You can use E-stat VCE to see the variance covariance matrix for all the estimates you just computed for any analysis. So that's helpful as well. Okay, let's look at another example building on what we did in HRS earlier. Okay, so remember, we computed means for 4 different subgroups defined by education. And suppose that we wanted to address the research question, do those with less than high school education have a significantly different mean income from those with 16 years of education or more? We want a formal comparison of those 2 groups, okay? So if you go back to slide 14, remember we ran this command that was looking at the financial reporters and giving us separate estimates for all 4 of these different subgroups, okay? So let's assume that this is the immediate last command that was run, and this is all the information that's been saved in memory, okay? So right after running that command, okay, we run lincom. Again, C dot is the continuous variable. We want the specific mean for education category 1.edcat, minus the specific mean for that continuous variable for education category 4. And back to Jones's question, this assumes that we want to report that difference as the difference between those with less than high school education and those with at least some college or with at least college education. That's the direction of the difference that we want to compute. Okay, so that lincom output is going to show us that exact difference, and here in this case it's negative because the mean for those with at least college education was so much larger than the mean for those with less than high school education. So again, the order matters. So the weighted point estimate of that difference is negative $712,000, a massive difference between these groups and their means. Then you see the standard error of that difference, 48,886. Okay, that is combining the linearized variances and the linearized covariance due to the cluster sampling. Okay. Then you see a 95% confidence interval for that difference, which again in this case clearly does not include 0. Okay, it's very far removed from 0. So we would firmly reject a null hypothesis that these 2 education categories have the same mean income. Okay, there's no evidence whatsoever to support that. Okay, everybody with me? So you can grab whatever point estimates you want from a prior subgroup analysis and do whatever you want with them. You'll get a confidence interval for whatever arbitrary function you define. Here we've just focused on differences in means, but you can use any combination that you want. Okay. So that's a very nice feature of Stata. How do we do this in R? So back to the same R code that we use for total household income. So we would say survey by, analysis variable, grouping variable, subset design object, survey mean is the function, get rid of missing values. We want to make sure to save the results of that analysis in this new object. Okay, so I'm calling that X515 because that was the exercise in the book that this is referencing. Okay, so in that new object, X515, that's where the means, the variances, the covariances, all those results of the analysis, that's where they're going to be saved. So we need to have that object to run the subsequent survey contrast command. To do this, the survey contrast is like the survey package's analog of lincom. Okay, so SVY contrast allows us to look at functions of estimates. Okay, so survey contrast again is yet another function in the survey package. There's a number of them that we're seeing now. First input argument is the object that contains the results of that by analysis. Okay, so that's why I want to emphasize we need to save that object, then reference that object inside SVY contrast. Once you have that object referenced, then you can have a list of different values that you're defining. Okay, so in this case, one of the things that we're outputting is the average of the 2 estimates. So that's one kind of combination you could use. So for example, if I wanted to make inference about 0.5 times the first estimate plus 0.5 times the fourth estimate, and I wanted to call that measure average, that's the syntax I would use. Okay? So I'm making a list of these arbitrary functions of the saved estimates, and I'm giving those output estimates unique names here, AVG. That's not an argument to a function. That's just an arbitrary combination I'm defining. So like if I wanted to do that in Stata, I would have said lincom 0.5 times the first estimate plus 0.5 times the fourth estimate. Okay? That's what AVG is. I'm most interested in this new metric called diff, D-I-F-F. I could have called it whatever I wanted to, where I'm looking at the contrast between mean 1 and mean 4. Okay? So mean 1 gets a coefficient of 1. Mean 4 gets a coefficient of -1. The middle two groups don't play into the calculation. That's why they each get coefficients of 0. Okay? Everybody with me the way this syntax is working? So I didn't need to have AVG here. I'm just illustrating a point. I can use whatever arbitrary linear combinations I want, same way I can within Stata. Okay? Diff is what I'm really interested in. And diff is then going to give me in the output the estimate of that difference, its standard error, and if I wanted to, the confidence interval. Okay? So that's how survey contrast works. We need the object contain the initial results. Then we need to specify the linear combination that we're talking about as part of a list that indicates all the combinations that we'd like to make inference about. Okay? That will give us the exact same output as what we're seeing with this data. Okay. Now, here is the ESTAT VCE for those 4 subgroups. So you can see most of the covariances of these subgroup estimates are positive, but there is in fact a negative covariance. So that covariance between subgroup 1 and subgroup 4 was in fact negative, which can happen. The key thing is that we just need to account for it, okay, when we do that variance calculation. And this is again all saved in the background when we use that kind of over option. So given this matrix, and this is just to make a point here, remember the standard error of this difference was 48,886. Given the information in that matrix, I can do that entire calculation. I just show what's happening in the background. So to get the standard error of this difference, I would take the square root of the variance of that difference. The variance of the difference is the variance of the first estimate plus the variance of the second estimate minus twice the covariance of the 2. Drawing those values from the previous matrix that I showed you, everything was multiplied by 10 to the 8th. So I just pulled that out here. I have 1.123 plus 21.6 minus twice negative 0.587. Boom. That's exactly what Stata is showing. So that's all that Stata is doing in the background. It's just carrying out that variance calculation. It's drawing on the inputs from the previous over option. Okay, so it's a very simple calculation that's being done here by lincom, but it helps us to make inference about arbitrary functions of these estimates. Okay, bear with me. All right, so that's what I wanted to cover today. Any general questions about percentiles, subpopulation estimation, or working with functions of estimates? Yep, is it?
Slide 22.
Yep.
For the sake of.
Yep.
For average, you see 0.5,
Yep.
0, 0.5.
Yep.
Now we have to appreciate between group 1 and 2.
Right.
So this is 0. What about if I'm going to change the values of 0.5 to 0.5? This means that I will give more weight.
Yeah. So like if you wanted to compute a combination of those 2 estimates where you give more weight to one group, say you want to give more weight to one group 1, you could say like 0.75, 0.25, right? Then you're giving 3/4 of the weight in that combined estimate to group 1. So you can choose whatever coefficients you want for that linear combination. You could use 0.19, 0.23, 0.57, 0.42. It'll still give you the variance of that combined estimate. So that's completely arbitrary, what we choose for those coefficients.
And if I add another one, if I compare between the 3, this is the case cannot be applied here, or because we need to use ANOVA, for example. Or
if you were interested in comparing group 1 versus group 3, you could say diff C 1, 0, -1, 0.
For a complexity.
Well, this is just for pairwise comparisons, right? Comparing three groups, again, you need that F test to see if there's any evidence of a difference overall. That's what we'll talk about next week. This is just for pairwise comparisons. Let's see, Jupiter and then Kier.
So for when we are doing the percentiles.
Yeah.
Some with I get the median.
A median, yep.
Then usually maybe people use like the interquartile.
Sure.
Just to measure the.
Right.
I don't know how do we sit. We do the same things.
Yeah, so when we looked at that example of quartiles here, your interquartile range would be Q75 minus Q25. So you would just need to compute weighted estimates of those quantiles and then look at the difference. That's going to give you your IQR. So you could use like the code we had here, 0.25, 0.5, 0.75, come up with those point estimates and look at their difference. The key is that you're getting a weighted estimate of that IQR, not the sample estimate. Yep. Kier?
But how do we recover the variance covariance for the SPY, UY, and R?
Let's see, so in your, within X, okay. So you'd have to look at, within that EX515 object, there's a number of different kind of subfields that you have to look at. So what you can do is when you save that EX515 object, type names, NAMES in parentheses, and then EX515. That'll give you the list of all the different components that are saved within there. And somewhere you're going to see like var cove or something like that. And then you can say EX515 $ V cove or whatever that name ends up being. I don't remember it off the top of my head, but you can say $ V cove, and that will give you that matrix in the output. Yep, it's part of that object. That's a general purpose thing within R. If you're curious what's contained within a given object, just use that names function. Other questions or comments on what we've talked about today? Okay, good. I have posted now the solution set for homework number 2. So feel free to take a look at that. Feel free to reply to Yang Chao and I if you have any questions about your homework number 2 marks. And also, again, for any questions related to the class or any submissions by email, please make sure to include me and Yang Chao. There were a couple of prospectus submissions that only went to Yang Chao that I didn't see. So always just make sure to include both of us on a class-related email. And that way we'll both see everything. So, okay. All right, I think we're all set for today. So we will see everybody on Friday for the lab, where we'll have more practice working with the different kinds of analyses we've been discussing this week. Okay. Okay, thank you.
Thank you.